Welcome everyone. Today we are diving into the world of Internet communication protocols. I'm Liu Zhao, and my partner Han Yuheng and I will cover not just the basics of Internet and its protocols, but we will take a closer look at the physical layer, understanding the technologies and innovations that drive data communication. Before we delve into the history and significance of Internet, let's understand what Internet is. Ethernet is a widely used technology for creating wide local area networks or lines. It connects devices like computers, printers, and routers within a localized setting, such as a home, office, or campus, using Ethernet cables. These cables carry data, enabling these devices to communicate and share information with each other. Ethernet operates on the principle of packet switching, which breaks down data into smaller, manageable packets before sending them to their destination. This method is efficient and reliable and forms the backbone of most network communications today. Internet, a revolutionary technology that has set the standard for network communications and shaped the digital world. Developed in the early 1970s at the Xerox Palo Alto Research Center by Robert and David, Internet introduced the groundbreaking idea of a shared medium for data transmission. This departure from traditional circuit switching methods to packet switching laid the groundwork for modern network communication. Internet has been instrumental in creating the interconnected world we live in today. It laid the groundwork for the global internet, breaking down geographical and political barriers, and enabling a new era of culture and social exchange. Furthermore, Internet's reliable and fast data transmission capabilities have directly contributed to the rise of e-commerce. It provided the necessary infrastructure for early digital marketplaces, revolutionizing how businesses operate and how consumers engage with them, thereby fueling the exponential growth of online commerce. In the industry sector, Internet is a key enabler of Industry 4.0, connecting IoT devices to create smarter factories that optimize production through real-time data. In agriculture, it lays the groundwork for precision farming, enhancing yield and stability through data-driven insights. Internet also plays a crucial role in developing smart cities, where its reliability and speed help manage urban infrastructure efficiency, promoting stability through optimized resource use and supporting green initiatives. Across these areas, Internet drives innovation and efficiency, highlighting its role as a cornerstone of modern industry and environmental sustainability. While Internet has revolutionized many aspects of our digital lives, it also presents several challenges that need careful consideration as we move forward. One of the most pressing issues is the digital divide, the gap between those who have access to modern information technology and those who do not, which can exacerbate social and economic inequalities. Cybersecurity is another critical concern, as the essential nature of Internet in numerous systems makes it a target for attacks. Necessary robust security measures to protect data and privacy. Moreover, the environmental impact of expanding network infrastructure, particularly its energy consumption, calls for sustainable practice and green technology solutions. Lastly, the rapid pace of technological advancements poses a challenge in maintaining state-of-the-art infrastructure, requiring continuous investment and adaptation to ensure efficiency and competitiveness. Addressing these challenges is crucial for the continued success and sustainable development of Internet technology. Now let's invite Yuheng to take over me to show the technology context of Internet.
Okay, I will introduce the technical part. Firstly, we are talking about the four basic elements of the Ethernet, and about the frame, I think it's the most important one. Frames in the Ethernet follows a specific structure. As we can see from this picture, the Primal was set up to give the hardware some startup time. It is followed by two 48-bit destination and source addresses. With these two addresses, the network will know where the frame came from and know where it needs to be sent. Together, they will ensure that the data is transmitted accurately from one device to another. After that, it's a 16-bit type field. It's typically used to indicate the upper layer protocol type, for example, the TCP or IP. After that, the data we need to transmit is about 46 to 1500 bits. The end of the frame is a 32-bit frame check sequence field. It's used to detect if an error is occurred in the data during transmission. After that, we will talk about the Media Access Control Protocol. As we mentioned before, the frame structure is defined by this protocol, and MAC has different roles in half duplex and full duplex operating modes. First, for the half duplex mode, we will introduce the collision detection. First, any device that is ready to send data must perform a carrier sense process, which monitors the network channel to find out if the channel is free. And if it's free, the device will begin data transmission, and if it's busy, the device must wait. This process is called deferral. And during the data transmission, the device continues to monitor the channel to detect possible clearance. If the clearance occurs, all devices will stop sending data immediately and wait for a random period of time before sending it again. This is a random backup, and this process will be repeated until the data is successfully sent. For the full duplex mode, things got different. The MAC protocol functions in three main ways. Firstly, we say the flow control. This is defined by a pause frame. The MAC layer at receiving device is responsible for calculating the pause time and generating the pause frame, while the MAC layer at the transmitting device will recognize the pause frame and respond to it by dynamically adjusting the data transmission rate so that the MAC protocol will achieve the purpose of traffic control. And the next is the quality of service. The MAC layer uses the priority code points in the Ethernet frame to mark and classify different types of traffic. This will ensure that the high priority data is processed faster with lower latency during the network congestion. The last one is the network security and isolation. This is achieved by adding VLAN tags to the Ethernet frames. The MAC protocol is able to segment network devices into different VLANs. Only devices within the same VLAN are allowed to communicate, so this will increase the security of the network. And after that, it's the signal components. It includes all hardware devices involved in the system. For example, the switches, the routers, and the twisted pairs. The last one is the physical medium. It refers to the cables or the radio waves. Next, we will talk about the Ethernet's role in the OSI model, which has 7 layers. Well, Ethernet is usually classified as the layer 2, the data link layer. This is because it provides the basic functions required for data communication in a local area network. For example, it transmits data frames, recognize MAC address, and detect errors. At the same time, Ethernet also involves some of the functions of the physical layer, the layer 1, such as the selection of transmission medium and the processing of physical signals. The upper layer of Ethernet is the network layer, which is used to handle network functions such as routing and forwarding of packets. Most widely used network protocols are TCP and IP. Okay, next we will talk about the Ethernet technology evolution. As we mentioned before, we know that Ethernet has completed the transition from half duplex to full duplex. In 1997, the new standard defines follow control for full duplex Ethernet, allowing simultaneous communication between a pair of base stations in a link. And this is the most important feature of full duplex model. This standard marks the official adoption of full duplex mode. It can be said that the full duplex mode enables Ethernet to achieve a good balance between speed, stability, and cost, which enhances its performance and range of applications. It also makes Ethernet stand out from many other network technologies, especially in network environments where high speed, low latency, and high reliability are required. And next, we talk about the full duplex auto negotiation system protocol. It is in order to better match devices from different operating modes. Ethernet introduced this system to detect and select communication speed, switch speed, and the duplex mode. Without user intervention, it will negotiate the optimal mode between devices. And the technology evolution also about the speed improvement. Since the Ethernet was invented in 1973, its rate has undergone a number of significant increases. The original Ethernet was only capable of 10 Mbps, and it was only suitable for early LANs. Then it was introduced fast Ethernet at about 100 Mbps. It was needed to increase the rate because it needed to meet the growing demand for data transmission. And in 21st century, it increased to 1 Gbps and then to 10 Gbps, marking Ethernet is entered into the area of high-speed networking. For now, it has become even faster to 40 and 100 Gbps. Rate growth cannot be achieved without improvements in the physical layer technology. We can say that the transmission medium has changed from UTP to twisted pair cable and then to be the fiber. Coding and signal processing techniques has also been upgraded a lot. Improvements in various technologies and the continuous updating for standards has combined to contribute the increase in rates.
The physical layer, or PHY, is where the digital meets the physical. Its main role is to convert digital bits into signals, be it electrical, optical, or radio waves, and vice versa. This layer encompasses everything from cables and connectors to the actual methods of transmission, forming the foundation of data communication in networks. The PHY layer operates under a variety of Internet standards, each tolerated for different transmission speeds and media types. For instance, 10BST allows for 10 Mbps over twisted pair cables, evolving to 100BSTX for 100 Mbps on Cat5, and further to 1000 BST for gigabit speeds on Cat5e. These standards ensure interoperability and performance across diverse network environments. At its core, the PHY layer uses encoding techniques to prepare binary data for transmission, which is then carried out via signaling. These processes are crucial for minimizing transmission errors and making efficient use of the available bandwidth, ensuring data arrives accurately and efficiently. The PHY layer faces challenges such as signal attenuation, interface, and inherent bandwidth limitations. Solutions include the use of higher-grade cables and advanced encoding techniques to improve signal quality, alongside devices like repeaters to extend transmission distance without losing data integrity. Encoding is a fundamental process within the PHY layer, transforming binary data into signals that can traverse our physical media, whether it be copper cables or fiber optics. Techniques like multi-state encoding have historically ensured data integrity and clock synchronization in Internet early days. As we progress to gigabit speeds, more sophisticated methods like NRZ and PM became essential, allowing us to encode multiple bits per symbol and drastically increase data rates without needing higher frequency signals. As we push for higher speeds in Internet networks, signal modulation plays a critical role in adapting our digital signals for the chosen transmission medium, efficiently using available bandwidth. Transitioning from baseband, which is prevalent in traditional Internet, to broadband allows for the transmission of multiple signals. Leveraging techniques like QAM, in particularly, enhances our data rates by modulating both the amplitude and phase of signal waves, exemplifying the PHY layer's evolution to meet the demands of modern network applications. The PHY layer's evolution is a testament to Internet's adaptability, with continuous advancements in encoding and modulation, ensuring that it meets the ever-growing demands for speed and reliability in network communications. This is particularly evident in the realm of cloud computing, where the PHY layer's capabilities underpin the performance and reliability of data centers. As we look to the future, the ongoing innovation in PHY layer technologies will be crucial in future-proofing networks, making Internet a cornerstone of emerging applications like IoT and 5G. The evaluation from fast internet to gigabit internet was marked by significant advancements, including the use of all 4 pairs in Cat5 cables and enhanced modulation techniques, pushing speeds to 1000 Mbps. The journey beyond gigabit internet with 10G base T reaching 10 Gbps over Cat6a sets the stage for future advancements. As we look towards 40 to 100 Gbps, the use of advanced modulation and fiber optics will be the key to meeting escalating data demand. Now let's look at the applications of Internet. Internet forms the backbone of networking within cloud computing environments, providing the high-speed, reliable connections essential for cloud services. At the heart of the setup is the PHY layer, which is crucial in maintaining signal integrity and ensuring that data speeds meet the rigorous demands of cloud operations. Cloud data centers have rapidly adopted higher speed Internet technologies, moving from 10 GBE to 100 GBE and beyond, to meet the backbone networking requirements. This leap is supported by PHY layer innovations, including advanced encoding and modulation, and the extensive use of fiber optics to achieve longer distances and higher throughput with minimum lattice. The PHY layer faces significant challenges in cloud computing, particularly in handling extremely high data rates and minimizing lattice across vast global networks. Solutions include the adoption of advanced technologies like PM4, which doubles the bits per symbol for increased data rates, the use of error correction codes to ensure data integrity, and the security development of network enhancers like repeaters and amplifiers to sustain signal quality over long distance. That's all. Thanks.